Welcome to the deep dive. So glad you're joining us. Okay, let's unpack this. When we hear about AI, the headlines often shout about these revolutionary models, stunning accuracy in labs. But what does it really take? To make that brilliant AI model reliably solve real-world problems day in, day out. Today, we're sort of pulling back the curtain. There's this fundamental shift happening. It's moving beyond just crafting the smart brain, the model, to engineering the whole system around it, the body, the nerves, everything. Our mission here in this deep dive is to give you a shortcut to understanding the complex architecture, the operational practices behind what people call production-grade AI. We're drawing on some expert guides, some blueprints here. Because, and this is the key thing, a highly accurate model, it can be surprisingly useless, really, if the machinery around it isn't built for the real world, the messy, chaotic real world.
What's fascinating here is exactly that worthless model idea you just mentioned. It's a bit counterintuitive, isn't it? Because we focus so much on the models, like intelligence score. But this isn't just about hitting a high score in a lab under perfect conditions. It's about delivering continuous, reliable value at scale every single day to actual users. And this shift, it really highlights that successful AI isn't a solo act. It takes a deep collaborative effort. You need data engineering, the ML modeling itself, and really robust software and systems engineering.
Yeah.
Think of it like building a race car. The engine might be incredible, right?
Yes.
But without a solid chassis, reliable fuel lines, a good pit crew, well, it's not winning any races. It just sits there looking impressive.
That's a really powerful way to put it in ecosystem. It highlights that interconnectedness, everything from the initial business idea all the way to that model performing out there in the wild. Our sources, they outline this journey. It's like a holistic ML system lifecycle, 5 interconnected phases, and crucially, they're iterative. It's not just a straight line.
Exactly. Not an assembly line, more like a loop, constantly feeding back. It starts with business and problem framing. Sounds obvious, maybe.
But crucial.
Oh, absolutely. This is where so many projects falter. You had to translate a business needs something broad, like boost user engagement, into a concrete, measurable ML problem.
Yeah.
Get this wrong. You might build a super accurate model that solves the wrong problem or has no real impact.
Right. All that effort kind of wasted.
Then comes data engineering. This is truly the backbone. Acquiring data, cleaning it, transforming it, preparing high-quality stuff. Because without good data, honestly, nothing else matters.
Yeah.
It's like trying to build a house on, quicksand.
And then you get to the part most people think of first, model engineering. Selecting the algorithm, training the model, optimizing it, but you have to do it with production in mind right from the start. It's not just about the highest score on paper.
No.
It's designing for resilience, cost effectiveness, continuous performance out there in the messy real world, even if, maybe, you trade a tiny bit of that theoretical accuracy for solid operations.
Precisely. And after that, it's deployment and serving. Getting that trained model actually into the software ecosystem so it can make predictions for users efficiently, reliably.
Making it real.
Making it real. And this leads to the final, absolutely critical phase, monitoring and iteration. This is where you watch it. You continuously track the model's real-world performance. You detect issues like drift, which we'll probably talk more about.
Definitely.
And you gather feedback from how it's operating. And that feedback loops all the way back. It informs and often forces you to revisit those earlier stages.
So you might need more data engineering.
Or tweak the model. Or even sometimes reframe the original problem entirely based on what you're seeing. That's why it's a cycle. Always learning, always adapting.
Okay, so to make this whole system, this whole machine, truly robust,
There you go.
to make sure it runs smoothly under pressure, the sources highlight 3 sort of foundational pillars: performance, scalability, and reliability. These are what make a system actually effective, not just clever on paper.
Right. Performance, that's all about efficiency. How quickly, how effectively does the system process requests? You think in terms of latency, the time it takes to get a prediction back.
Like for recommendations, right? Needs to be fast.
Exactly. And throughput, how many predictions can it handle per second or per minute? For real-time stuff, low latency is just non-negotiable. It impacts the user experience directly.
And scalability, that's about handling growth, right?
Yeah.
More data, more users.
Yeah, handling increasing workloads gracefully. And it has 2 sides. There's ML system scalability. Can you train on bigger data sets? And then there's software system scalability. Can your deployed system handle more users, more prediction requests without falling over?
You need both.
You absolutely need both. You need to
Yeah.
grow with demand. Otherwise, your brilliant AI just buckles under its own success.
Okay, and the third pillar, reliability.
Reliability. which is the system's ability to operate correctly consistently, even when things go wrong. Because let's face it, individual components will fail sometimes.
It's inevitable in complex systems.
Totally. So this means building in fault tolerance. Systems that can handle hiccups, recover gracefully, prevent those costly outages. These three pillars, performance, scalability, reliability, they really separate a clever lab experiment from a robust product-ready system that delivers value day in and day out.
You mentioned systems breaking, and it's interesting. The most frequent point of failure, it's often not the complex model itself. It's something more fundamental,
Right.
the data backbone.
Ah, yes.
People assume the model's the tricky part, but our sources say data pipelines, they cause a huge percentage of production ML failures. They call them the silent killer.
That's a good term for it.
Exactly.
Catastrophic errors in predictions, and maybe you don't even notice right away. It's insidious.
So how do you fight that? How do you build resilient data pipelines?
Well, several key strategies. First, diverse ways to get data in. You use batch ingestion for big historical chunks like updating a product catalog overnight. And you use real-time streaming ingestion for immediate stuff. User clicks on a website, things happening right now.
And often you combine them.
Often you combine them, yeah, in what's called a hybrid lambda architecture. Think of it like having two lanes on a highway. A fast lane for the real-time data gives you quick answers, and a slower, maybe more thorough lane for the batch, historical data. That ensures accuracy and completeness over time.
So you get speed and accuracy, best of both.
You try to, yes.
Yeah.
Then there's automated data validation and quality. This is like a really strict gatekeeper for your data. It does essential checks. Schema validation is the structure right. Data types correct. Rule-based validation for business logic like a price should never be negative, right?
Makes sense.
Plus, continuous monitoring. Is the data complete? Is it consistent over time?
And the core transformation part.
That's robust ETL and data transformation. ETL, extract, transform, load. This is where you automate the process of cleaning that raw data. Normalizing features, encoding things like categories into numbers the model can understand, feature engineering, crafting the data into the perfect shape. And critically, these processes need to be reproducible and versioned. You need to know exactly how the data was prepared.
Tools help here, I imagine.
Oh, definitely. Workflow orchestration tools like Apache Airflow is a common one. They manage these complex, dependent data flows, make sure step A happens before step B, handle failures, retries. It's crucial plumbing.
Okay, solid data pipeline built. But what if the model, despite all that good data and training, still makes a prediction that's just weird or even dangerous?
Ah, right. This brings us to a really neat concept, the hybrid intelligence stack.
Hybrid intelligence sounds intriguing.
It is. It's about strategically combining the learning power of ML models with the clear, transparent logic of deterministic, rule-based systems, old-school rules, basically.
So AI plus explicit rules.
Exactly. You use the rules as sort of safety harnesses.
Right.
Or guardrails, to prevent the ML model from going completely off the rails, making absurd or harmful predictions. It enhances reliability and builds trust.
How does that work in practice? Are there common ways to set this up?
Yeah, there are a few common architectural patterns. You might have rule-based pre-processing. So rules filter or transform data before it even hits the ML model. Simple checks get handled up front.
Okay, cleaning up beforehand.
Right. Or you can have rule-based post-processing. These are the guardrails after the prediction. They validate the ML output. They can even override it if it violates some hard business constraint.
Like the example you gave earlier, if an ML model predicts a super low price.
Exactly. A rule could say, hang on, if the predicted price is below our cost, nope, set it to cost. The rule gets the final say in critical spots. It acts as a veto.
That makes a lot of sense for critical applications.
Definitely. Then there's another pattern, ML, as a feature for a rule engine. Here, the model's output may be a probability score, like how likely a customer is to churn doesn't make the final decision. It just becomes another input, another piece of information for a larger, perhaps human-designed rule engine that considers multiple factors before deciding what action to take.
So the ML provides insight, but the rules make the call.
Precisely. And finally, there's rule-based fallback. Simple idea. If the ML model isn't confident about its prediction, or if it fails entirely for some reason.
Which can happen.
The system gracefully switches over to a simpler, safe, rule-based alternative. Ensures you always get some reasonable output, even if it's basic. The system doesn't just go dark.
That seems really practical.
It is. And what's interesting is that this boundary between rules and ML, it's not fixed. Systems can evolve. Start mostly rule-based,
Hmm.
gradually add more ML as you get more data, more understanding. The sources even mention things like neurosymbolic AI as sort of the next frontier here, trying to build rules directly into the neural network's learning process, making AI that's both smart and inherently trustworthy from the start.
Fascinating stuff. Okay, so we have the architecture, the data, maybe some hybrid intelligence. Now let's talk more about tuning the brain itself, the model. We've already
Sure.
said it's not just about accuracy scores. Selecting a model for production needs a multi-factor view, doesn't it?
Absolutely. It goes way beyond just picking the algorithm with the highest score on a benchmark. You start with the problem type, obviously. Is a classification, regression, something else? But then you have to look hard at your data
Like
characteristics.
how much data you have.
Exactly. Small data sets. Simpler models are often better, less risk of overfitting. Massive data sets. That's where deep learning can really stretch its legs. And the data type matters hugely. Tabular data, like spreadsheets, often works well with tree-based models like random forests or gradient boosting. Unstructured data images, text, that usually screams deep learning.
And there are the practical constraints, the operational constraints.
Right, latency requirements we mentioned. For real-time use, you might need a much lighter, faster model, even if it sacrifices a tiny bit of accuracy.
And just the cost, right? Computational
Yep.
resources.
What hardware do you actually have? What's your budget for training? And just as importantly, for serving the model running at 24/7 to make predictions. That cutting-edge massive model might be technically best, but if it's too slow or costs a fortune to run, it's not the right choice for you.
And you also mentioned business and regulatory constraints. Explainability comes in here, right?
Hugely important.
Yeah.
Interpretability and explainability, especially in high-stakes areas, finance, healthcare. You need to understand why the model made a certain decision.
The black box problem.
The black box problem. This often leads to a trade-off. You might deliberately choose a simpler, more transparent model, like logistic regression or a decision tree, over a super complex neural network, even if the complex one scores slightly higher, simply because you can explain the simpler one's reasoning. So the optimal model isn't just the most powerful one. It's the one that best fits all these real-world constraints: data, operational, business, regulatory.
Okay, so you've chosen your model type. Now you need to tune it, get the best performance out of it. Hyperparameter tuning. The sources mention moving beyond just guessing or brute force grid search. There are smarter ways now.
Yeah, grid search and random search can be really inefficient, waste a lot of computation. More advanced methods are much better, like Bayesian optimization. It intelligently chooses the next set of parameters to try based on what it learned from past results. It focuses the search on promising areas,
Faster discovery.
much faster. Then there's gradient-based optimization for some types of models and parameters. It can sort of learn the optimal settings by following the gradient, like rolling downhill on the performance surface. And evolutionary algorithms. These mimic natural selection. They create a population of configurations, evaluate them, breed the best ones, introduce mutations, evolving towards better solutions over generations.
Sounds complex but powerful.
It can be. And a really practical one is early stopping algorithms, like hyperband or ASA. The basic idea is clever. Train lots of different model configurations, but only for a very short time, a few epochs.
Okay.
Then throw away the ones that are doing poorly right away and allocate more training time, more resources, only to the ones that look promising early on.
So you don't waste time fully training models that are clearly duds from the start.
Exactly. It speeds things up significantly, avoids wasting compute cycles on dead ends.
So you've tuned it, but sometimes the model is still too big or too slow for where you need to run it, like on a phone.
Right. Model compression becomes really important then, especially for edge devices or applications needing super low latency. There are several techniques. Pruning is one. For neural networks, it basically identifies and removes redundant connections or parameters, snips them away often without hurting performance much. Makes the model smaller and faster.
Trimming the fat.
Kinda, yeah. Then there's quantization. This reduces the numerical precision used to store the model's weights. Instead of using, say, 32 bits for each number, maybe you use 8 bits, or even fewer. Makes the model significantly smaller, faster to compute, uses less memory. There's usually a small trade-off in accuracy, but often it's worth it.
And I saw knowledge distillation mentioned too. That sounds interesting.
It is. The idea is you have a large, complex, very accurate teacher model, but it's too slow or big for deployment. So you train a separate, much smaller, simpler student model. And the student's goal isn't just to learn from the data, but to learn to mimic the outputs of the big teacher model.
So the student learns the teacher's knowledge.
Exactly. It effectively distills the complex knowledge from the teacher into a more compact form. So you get a smaller, faster model that performs almost as well as the big one. Really useful for deployment constraints.
And beyond just performance, there's that understanding piece again, making the model less of a black box. Explainable AI or XAI.
Crucial for trust, like we said, and for debugging, fairness analysis. Lots of reasons. There are techniques like LIME. That stands for Local Interpretable Model Agnostic Explanations.
Local,
Yeah.
meaning for one specific prediction.
Exactly. LIME helps you understand why the model made a particular prediction for one specific input instance. It works by essentially building a simple, transparent model, like a linear model, that approximates how the complex model behaves just in the local neighborhood around that one instance. It tells you which features push the prediction one way or the other for that specific case.
Okay, so LIME is local. What about understanding the model more generally?
That's where techniques like SHAP come in. Shapley additive explanations. It's based on game theory concepts, actually. SAP calculates the contribution of each feature to the prediction, considering all possible combinations of features. It gives you these SHAP values for each feature for each prediction.
So it's also local.
It provides rich local explanations, yes. But you can also aggregate these SHAP values across many predictions to get powerful global explanations, like which features are most important for the model overall, across the entire data set.
So SHAP gives you both local and global views.
Right. It's become quite popular because it's theoretically well-grounded and often provides really insightful explanations. Building that stakeholder trust through explainability is just paramount.
Okay, we've covered a lot of ground on the system, the data, the model itself. Finally, we get to MLOps, machine learning operations. If the model is the engine, architecture the chassis. MLOps is like the pit crew, the maintenance team, the whole operations center, right?
That's a great analogy. MLOps is the engineering discipline that manages the entire ML lifecycle in production. It's about keeping these AI systems healthy, performing well, and continuously improving. It's where the rubber really meets the road.
Where does it start? Deployment.
Yeah, deployment strategies are a key part. First, deciding where to run everything. On-premise servers, in the cloud, a hybrid approach.
Pros and cons to each.
Definitely. On-prem gives you maximum control, data sovereignty, but it's a big upfront investment and you manage everything. Cloud offers amazing scalability, elasticity, pay-as-you-go, but you rely on the provider. Hybrid tries to balance, maybe keep sensitive data on-prem, but use the cloud for heavy computation. The choice depends on your needs, budget, regulations.
And once it's deployed, you can't just leave it, right? Models degrade.
Absolutely not.
Yeah.
This leads to the heart of MLOps. Automated retraining pipelines or continuous training, CPI. The real world changes. User behavior shifts, data patterns evolve. That model trained on old data. It will get stale. It will degrade.
So you have to retrain periodically.
You have to retrain on fresh data. And MLOps is about automating this. Building pipelines that can automatically pull new data, retrain the model, evaluate it, and potentially deploy the new version. And a critical piece here is versioning everything. The code used for training, the dataset itself, the resulting model artifact, the parameters. Everything needs a version so you can reproduce exactly what's running, or roll back if needed.
Complete reproducibility.
Essential. These retraining pipelines can be triggered on a schedule, like weekly, or maybe by specific events, or even automatically when monitoring detects performance degradation.
Which brings us to monitoring that degradation, detecting drift.
Right. Vigilance in production. Detecting and mitigating model drift. This is huge. Models decay. There are different kinds of drift. You have the data drift, the statistical properties of the input data change, maybe your user-based demographics shift.
How the inputs change.
And then there's concept drift. This is more subtle. The relationship between the input features and the thing you're trying to predict changes. What used to signal fraud might not anymore because fraudsters adapted.
The meaning changes.
Exactly. Proactive monitoring for both types of drift is absolutely crucial to maintaining performance.
How do you monitor for it? Are there specific techniques?
Yes, several sophisticated ways. Statistical tests are common. Things like the Population Stability Index, PSI. It quantifies how much the distribution of a variable has shifted between, say, the training data and the current live data. Or the Kolmogorov-Smirnov test, another statistical method to compare distributions.
So mathematical checks.
Mathematical checks. You can even get fancier. Some teams trained a domain classifier. It's literally an AI model whose job is to tell you if a piece of incoming production data looks like it came from the original training distribution or if it looks different.
Using AI to monitor AI.
Pretty much.
Uh-huh.
And when drift is detected above a certain threshold, it can trigger alerts for the team to investigate, or, like we said, even automatically kick off a retraining pipeline.
Okay, so you detect drift, you retrain, you have a new model candidate. How do you know if it's actually better in the real world?
The ultimate test, A/B testing and experimentation. You never just push a new model straight to all users. First, you evaluate it offline, using historical data and metrics. Does it look promising?
If yes, then what?
If yes, then you promote it to an online A/B test in the live production environment.
How does that work?
You split your users randomly. A control group keeps getting predictions from the current model, Model A. A treatment group gets predictions from the new candidate model, Model B. Then you track key business metrics for both groups. Click-through rates, conversion rates, user engagement, revenue, whatever matters for that specific application.
And you see which model performs better on those real business goals.
Precisely. Does Model B genuinely lead to better outcomes? It's the gold standard for measuring the actual causal impact of your change. Only if the A/B test proves its value do you roll out the new model to everyone. It proves real-world value, not just theoretical improvement.
Wow. Okay. So what does this all mean? We've covered a huge amount. We went from understanding this whole iterative ML lifecycle, its pillars, performance, scalability, reliability. We dove into the critical, maybe underestimated data backbone. We looked at the clever hybrid intelligence stack, blending rules and AI, the details of model engineering, selection, tuning, compression, explainability, and finally, landing on MLOps, deployment, monitoring, retraining, A/B testing. I think the big takeaway is successful AI. It's really about architecting and nurturing the entire system. It's not just building one smart model in a vacuum. It's like building a robust, adaptive digital organism.
I think that's exactly right. And if we connect this to the bigger picture, this whole conversation really highlights how the role of AI and ML professionals is changing. They're moving beyond being just pure modelers, focused only on algorithms. They have to become true systems thinkers, architects,
Balancing different concerns.
balancing all those things we talked about. Algorithmic sophistication with data pipeline reliability, predictive power with interpretability, development speed with long-term operational stability and cost. It's this holistic view, like building and maintaining that high-performance machine. And this raises an important question. For you, the listener, as AI gets embedded more and more deeply into everything business, society, how does understanding this system-level thinking, all this stuff behind the scenes, how does that change how you might approach or evaluate AI solutions, whether it's in your job or even just apps you use every day? Do you start looking past the flashy demo? Do you start wondering about the data pipelines, the reliability, the MLOps practices holding it all together?
That is a really great question to ponder. Something to think about long after this deep dive ends. Thank you so much for joining us today. Until next time, keep that curiosity going, keep exploring. And remember, the real magic of AI is often hidden in that complex, careful engineering underneath.